Good morning. I want to continue talking about graphing absolute value functions today. We began talking about this yesterday. And today I want to look at the equation f of x equals negative times the absolute value of x plus 2 minus 3. So that's the graph that we're going to do. Only I want to show you another way of dealing with this. Some of you are visual and you like the thought of taking the graph and moving it around with the transformations that I was showing you yesterday. But some of you are more like algebraic thinkers. So you guys have had algebra and geometry now. Some of you probably like algebra better and some of you probably like geometry better. So the geometry people tend to like the transformations idea of just take the picture, slide it around, tell me what to do to it. But the algebra people probably will like what I'm going to show you now. So you can always use a table of values in order to find some ordered pairs and get your sketch for your graph. So let's say you didn't remember about the transformations. You just wanted to go with finding some points. So I just wrote down some numbers here. So I'm going to start with 0. I'm going to take that 0, plug it in for my x value. 0 plus 2 would be 2. The absolute value of 2 is still 2, but then there's negative out front. Now this negative is not affected by the absolute values because it's outside of it. The absolute values can't reach it. So after that, we'd be at negative 2, and then there's a minus 3 on the back end. If you want to think of that as adding the opposite, you could say plus a negative 3, so you would be at negative 5. Now let's take a 1 and plug it in here for the x. So 1 goes right here. 1 plus 2 is 3. This negative turns that to a negative 3 because the absolute value of 3 is still 3. Then there's a negative on the front of it. So negative 3 plus negative 3 would be negative 6. Now I'm going to take the 2, plug it in for the x. 2 plus 2 is 4. Absolute value of 4 is still 4. There's a negative out front, so you're at negative 4. Add negative 3 to that. That makes negative 7. I'm going to take a 3, plug it in here for the x. 3 plus 2 is 5. The absolute value of 5 is still 5. There's a negative out front, so that's turning it to a negative 5. Add negative 3, you'd be at negative 8. Okay, now I'm going to switch gears and look at some negative values. So I'm going to take a negative 1, plug it in here for the x. Negative 1 plus 2 would be 1. So we're taking the absolute value of 1. How far is 1 away from 0? That would be 1. There's a negative out front of that, so that turns it to a negative 1. We add a negative 3. That makes negative 4. I'm going to take a negative 2 and plug it in here for the x. So negative 2 plus 2 makes 0. The absolute value of 0 is still 0. Negative 0 is still 0. And then we need to add negative 3. So 0 plus negative 3 gives us negative 3. I'm going to take this negative 3 and plug it in for the x. So negative 3 plus 2 would be negative 1. Now when you take the absolute value of negative 1, that turns it to a positive 1 because negative 1 is 1 unit away from 0. Remember, when we talk about distances, we respond with a positive. But then there's this negative out front, so it turns it back to a negative 1. Plus negative 3 gives us negative 4. Negative 4 is going to go in for my x value. So negative 4 plus 2, that would be negative 2. The absolute value of negative 2 would be a positive 2. This negative sign out front turns it back to a negative 2. And then I add negative 3. So that would be negative 5. So I think this is enough points here for us to get an idea of what this is going to look like. So let's see. Put my x and y axes on here. Oops, that was a little crooked. Okay, so I'm going to plot some of these points so we can see what this is going to look like. 0, negative 5, 1, 2, 3, 4, 5, 1, negative 6, 1 in the x direction, 6 down, 2, 7, 2, 1, 2, 3, 4, 5, 6, 7, 3, negative 8, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. Then I switched gears and went to an x value of negative 1, so that's 1 step to the left. And that makes me go 4 steps down. 1, 2, 3, 4. Negative 2, negative 3 would be over 2 and down 3. negative 3, negative 4 would be over 3. 1, 2, 3, down 4. 1, 2, 3, 4. Okay, now I'm starting to see the V shape emerge. So this is an absolute value function. So I knew there was going to be a V somewhere. I just hadn't seen it till just now. The last point I have is negative 4. 1, 2, 3, 4 in the x direction, and then down 5. 1, 2, 3, 4, 5. Okay, so I can tell where my V is going to go. It's going to go like this. So I'll sketch that on there. And now I want to show you the link between that and the transformations that we've been talking about. So this is where our A value goes. Oh, you can't see that. A value. Probably shouldn't have used green on this whole thing, should I? Sorry about that. This is the H. Remember, it's supposed to be x minus h, and then the plus k is on the back here. Okay, so y equals f of x equals whatever. So that's the form. So these are absolute value signs there. So our h value, to link it to the transformations, okay, so this is weird. It says x plus 2, and remember how we've talked about there should be a minus sign in the setup? I'm going to take that plus sign and break it down into a double negative. I could combine them back and make a positive, but I'm disassembling them right now so I can see what the h value is. So this h value here is a negative 2. So that means from vertex where it would have been on the parent function, oops, let's see, not like that, that's what the parent function would look like, that y equals absolute value of x1 that we graphed first yesterday. That vertex was here at the origin. I need to go 2 steps to the left, and then this k value is negative 3. That's why you see the vertex 3 steps down. So that kind of makes sense where that vertex is coming from. And then the reason that this thing faces down is if you look at your a value here, a is a negative. You could put an understood 1 if that helps you see it better. It's a negative, and that flips the graph upside down. It does a flip vertically. So that's why you see it heading down in this case. So you can graph by using your transformations, or you can just graph it from a table of values, and then you can see the connection to the transformations. Either way is fine. They're both correct. Now let me show you where you can use this in a problem. So you'll have one problem like this on your set that you're going to do. So this says, this is about light reflection. So a beam of light shines from a spotlight that is 10 feet off of the floor. It reflects off of a mirror on the floor that is 15 feet from the wall that the spotlight is on. How high does the light hit the other wall that is 8.5 feet from the mirror? Okay, so it's about a spotlight hitting a mirror and bouncing back, okay? I read that way too fast for you to actually tell what's going on, so I'm going to slow it down, and as I slow it down, I'm going to draw it, because this is describing a picture, and so in math, it's going to be real helpful. If they start describing something that you should be able to see, you want to be able to see that. So I'll sketch it as we go this time. So a beam of light shines from a spotlight that is 10 feet off of the floor. Okay, so here's the floor. Oh, I can't see that. Here's the floor. And so here's going to be my wall. Is it bad that I have to label my wall so you know it's a wall? The spotlight is 10 feet off of the floor. So we're going to put the spotlight right here. So that's the spotlight. And that's 10 feet. So I'm going to draw a bracket over here. That's 10 feet. Now it's going to shine on the floor, and it's going to hit a mirror on the floor that's 15 feet from the wall that the spotlight is attached to. Okay, so if I go 15 feet over, so from here to like, we'll say that's 15 feet. Here's where the mirror is, okay? So that right there is the mirror. Okay, so it's 15 feet from the mirror. So the light is gonna come down like this. From the spotlight, it's gonna like hopefully that's straight. It's going to hit the mirror. Now, when light hits a mirror, what happens? Well, it bounces back, and it bounces back at the same angle that it bounced onto the mirror at. So it's going to bounce back. See if I can freehand it. Something like this. But there's another wall. It says that, let's see, how high does the light hit the other wall? That's 8.5 feet from the mirror. Okay, so we'd be talking from here over to this other wall. So this is 8.5 feet here. So this distance is 15 feet, and then over on this side it's 8.5 feet. So you can tell it's not going to hit as high on the wall as it was where the spotlight was attached, because the mirror is closer to that side, or I should point that way, I think, closer to that side. So anyway, do you see that the shape is going to kind of remind you of this parent function of absolute value? We're going to be able to explain this by using an absolute value equation to link it. So we have a mathematical model to go by here. So what I'm going to do is I'm going to put this coordinate plane, this xy, oh, it glares. Let's see if I do this. Does that help? No. Just a minute. Okay, that's a little bit better. So I'm laying this xy coordinate plane. See, I have this clear xy coordinate plane that I'm going to lay over the top of it. And I'm going to place it so that the y-axis is that wall that we have the spotlight attached to, and then the x-axis is the floor there, okay? So we've got it on here. Now I want you to notice the vertex. Do you see this vertex here? It's not where the parent function vertex is, because the parent function vertex would have been over here on the origin. So it's moved, hasn't it? Well, which way has it moved? Good job, it's moved to the right. And how far to the right has it moved? Yes, you're correct. It's moved 15 feet. So what we're going to do is we are going to write it like so. So y equals x minus. So it's moved 15 feet over, so I'm going to put a 15 in here for the h. Notice the minus sign is there because it's always there in the setup. The 15 is a positive 15 because it's moved to the right. So let me lay this back on here for a second so you can see it again. So if the parent function vertex would have been right here, we've moved it to the right 15 feet. Has that vertex gotten moved up or down at all? I know the glare is kind of right there, isn't it? No, it's just sitting right there. That mirror is the vertex of this absolute value function, and it's sitting right there on the ground. So my k value is going to be a 0. So I'm going to put that down here. So since it's plus 0, you honestly don't even need to write that part because adding 0 doesn't do anything mathematically. So I don't really need that part there. So we've talked about the h, we've talked about the k. Now we need to talk about the a value. Okay, so a is what adjusts how steep it is. So remember, on this parent function, you see it going up 1 over 1, up 1 over 1 in both directions. So that's what it looks like if it's the parent function. So I wonder if this one that we're looking at has gotten any steeper or flatter than what we are seeing on the parent function. So let me lay this back on here again. Okay, so my vertex is here at the mirror, okay? So I want to see how steep this line segment is. So I'm going to choose to use this point where the spotlight is anchored to the wall. And I wonder how much I rise and how much I run to get over there. Well, do you remember how high the spotlight is on that wall? Yeah, it's 10 feet up, so it's up 10. And then if I went up 10 feet from the mirror, how far would I have to go over to get to the spotlight on the wall? Well, that would be 15 feet over. So our A value here is going to be a 10 over 15. So it's not as steep. This picture is not as steep as the parent function is because this fraction is less than 1. And so it's flattening it out kind of. It's compressing it. Now those numbers, 10 and 15, are both reducible by 5s. So I would like to reduce this. Y equals, that would reduce to 2/3. X, oops, you can't see that, can you? X minus 15. Okay, so there's a cleaned up version of it. Now here's what I really want to know. I really want to know, where is this point of light on the wall, the opposite wall, that's reflecting off of my mirror? Where is that hitting it at? Okay, so that's what I want to know. Well, how far over are we, like, from the origin? Like, could you give me, think like an ordered pair. In fact, let me lay this back on here so you can see it again. Oh, shoot, my sticker covers it up. Okay, so just remember, this is your y-axis, this is your x-axis. So to get from this origin, this would be the origin here, how far over do I have to go? Well, I got to go 15 feet just to get to the mirror, and then I got to keep walking another 8.5 feet to get to the other wall. So we'd be talking about 23.5 feet. That would be your x number. Remember, x tells you left and right movement. And I want to see the y value that goes with that. So I'm going to take this 23.5 and plug it in for this x right here. So right here, for my x, that's where I'm going to put my 23.5. So let's see, where's my calculator? So, I don't know if you'll be able to see this or not. I think it'll show up. So I'm going to take 23.5, and I'm going to subtract the 15, because that's together inside the absolute values. I get 8.5. The absolute value of 8.5 is still 8.5. And then I need to multiply it by this 2/3 out front. So I'm going to say times 2 divided by 3 is 5.6 repeating. So that would be, that's 2/3 is what that is as a fraction. 5 2/3 feet up. So that point of reflection would be a little bit above my head because I'm not quite that tall. So yeah, 5 2/3 feet is where that point would hit the wall. So you're going to have a problem that's kind of like that. Instead of light, though, it's going to be a pool, billiards, I think is the word, ball bouncing off of the side, and you're going to see if you can hit it into the pocket with the angle that you take. So you can think about putting a graph over the diagram that you draw, so you can think about it like your absolute value functions. So I think that is everything. So remember that Jesus loves you, and so do I, so do your math.